All right, so what we looked at, oh no. It works. I just mash the keyboard until it works. So, what we're doing is taking the atomic orbitals, okay? And in all of the cases that we're concerned about, the atomic orbitals we're looking at are S and P. Right? And in particular, we're looking at the 2s and 2p. Okay? And we're just mashing those orbitals together until we have the proper orbital alignment and the orbital count that we need to explain the bonding pattern that we're looking at. Okay, so when it comes to methane, when we draw our structure for methane, we have 4 groups of electrons. Those 4 groups, based off of Vesper models, all have to be 109.5 degrees away from each other. I know I need 4 atomic orbitals from carbon to make those bonds. Right? Well, I have 4 atomic orbitals. They just don't match the bond angles I need. Okay? So I'm taking the shapes, the spheres, the probabilities of those orbitals, and I'm just going to put them all together and make new stuff. Right? You don't like the game, you quit the game, and you make your own rules. That's what's happening. Okay? At its simplest level. So in that process, to get those 4 new orbitals, I have to use all 4 of my atomic orbitals. Okay? And I make these 4 new orbitals. Okay? And I'm going to name those orbitals SP3. Okay? The reason SP3, that's what I use to make them. That's the order of that name. So that first orbital is called SP3. That third orbital is called SP3. They're all SP3. Every single one of those. All right. What happens if we, instead of looking at methane, we looked at borane? Don't worry about the naming on that. BH3. Well, how many groups of electrons are on the boron? 3. So I need 3 atomic orbitals to explain the molecule and the shape that we're seeing for borane. Do we have 3 equivalent atomic orbitals? Here's our atomic orbitals. Do we have 3 equivalent atomic orbitals? Yeah, right? What are they? The p orbitals. So I could just say, well, I don't need to hybridize anything. I'm just going to use the p orbitals. Except, what's the bond angle between the p orbitals? 90 degrees. And the bond angle in borane, 120. So I can't use just the p orbitals because it doesn't accurately represent the bond angle or the geometry of that molecule. So I'm going to have to hybridize. Okay? With the first example, I just picked all of the orbitals because I know I needed to use all of them. This time I don't have to use all of them. So which 3 do I choose to use? Okay? Could be my choice. I could just take all 3 p orbitals and mash them all together to end with 3 new hybrid orbitals. Okay? That actually doesn't make sense based off of your understanding of atomic theory. That's kind of bizarre. I seem to be making a lot of presumptions about your understanding of atomic theory, aren't I? Hydrogen has 1 electron, right? Where does that 1 electron go? You can do better than that. Where does hydrogen's 1 electron go? Suggestion was the s orbital. And I said you can do better. What was it?
S1.
Close. Flip the 1 in the s. The 1s. It goes into the first energy level, s type. Okay? Nobody said 2p. Nobody said 4s. Why not? Couldn't I have placed the electron there? I would need to add a lot of energy to get it there. The placement of our electrons has to do with energy. And our first placement is lowest energy. If I just take the p orbitals, am I taking the lowest energy? No. I will always start my hybridization using the s orbitals because they are lower in energy than the p. Okay? So I'm going to take the s. I needed 3, right? One of them has to be s. Now what do I need? I have to add in 2 p's. Okay? Because I need 3 orbitals, I have to put in 3 orbitals. So I'm going to take the 1s, 2 p orbitals, I'm going to mash them all together, and I'm going to make 3 new orbitals. Those 3 new orbitals are all going to have a new name because they aren't s and they aren't p. Could I call them sp3? Okay. Some people are yes, some people are no. No, you can't call them sp3. Why not? I only used 2 p orbitals. I didn't use all 3. So I can't call them sp3. So what am I going to call them? sp2. Okay. And now I get sp2. So there are my 3 sp2 hybrid orbitals that I have created by mashing together those orbitals. Right? There we go. 3 new ones. Okay. I can't create or destroy matter, though. Our orbitals are the equivalent of matter or energy. Stick with energy. Okay. There's that one leftover p orbital, right, that I did not hybridize. What happens to it? It stays. Nothing happens to it. It's left over. So when I now go through and look at the diagram for that boron molecule, it's going to have 3 hybrid atomic orbitals to properly explain the VSEPR model. And it's going to have 1 p orbital left over. Okay? If we go back and look at that borane structure, where are the electrons placed around the borane? Horribly vague question. I might regret that. Tell me where they're placed. I don't see any orbitals in the borane structure, so I'm going to say no on that. They're in the bonds. Okay, that's what I wanted. Okay, they're in those bonds, right? Okay, those bonds are made up of orbits. And in case of the borane, the orbit that borane is contributing is what to that bond? What orbital is the borane contributing to make each of those bonds? If it's a p orbital in each of those cases, what should the bond angle be? 90. It's not 90, it's 120. So it ain't p. sp2. That's one of those hybrid orbitals, right? How many electrons in that first bond? 2. That one? That one. How many electrons are on the borane? 6. How many electrons go into that p orbital? 0. Borane doesn't have any more electrons. We can't add more electrons to the borane molecule because there's literally no more electrons. But I do have this leftover p orbital. Why does that become interesting? That p orbital has nothing in it.
What about core electrons?
Core electrons we don't care about. Those are lower than this system, so also irrelevant. Those are empty, right? Can I now predict something about borane's reactivity? It's more reactive, okay, and I heard a yes, so good. Yes and more. How is it more reactive? What could it do? It could accept more electrons. It can accept more electrons because there's a p orbital left over that has nothing inside it. This borane structure can add more electrons to it, which is why we can end up with borohydride. The molecule borohydride exists where this hydrogen brings in 2 electrons and drops them into that p orbital. Is that going to change the VSEPR model? Yep. Is that going to change our hybridization? Yeah. Okay. But what we're looking at is in the process of this happening, that bond forming, those electrons are going into the p orbital, which causes all sorts of weird stuff to shift, and we end up with our sp3 hybridization. But we now have a way to explain how that structure can exist and how it's coming about. I'm putting in electrons, right, that were left empty. There's a place to put them.
Is that the same thing with breaking octets, but the orbital?
Breaking octets is a different thing. Because breaking an octet means you're putting in more than 8 electrons.
Right.
How many electrons can I fit in this? 8. How many can I fit in the SP3? 8. So when you're breaking octet, you're saying, I'm going to put 2 more electrons in. Into what? There is literally no space to put them. The electrons can't exist in this picture. So when you draw a carbon that has 5 bonds or 10 electrons, you're saying you somehow put those electrons into an orbit that doesn't exist. That's why it's bad to exceed octets. Why can the S was a bad term, the sulfur, why can sulfur exceed its octet? It has access to the d orbitals. Those d orbitals, which happen to be all empty, which means could you put 2 more electrons in? Yes. Those d orbitals are available and allow you to now expand the octet. You can't do that for carbon because there isn't an orbital system that's available to place those electrons. There's literally no more space. Okay? I'm really not going to like drawing this one, but I'm going to do it anyway. If we try to describe what happened with this magnesium, okay, as a Lewis structure, because I now just said the word Lewis structure, I got to draw all the stupid dots. Would this be a valid Lewis structure? Yes. Is it a good structure to draw? No. Lewis doesn't explain anything to do with shape. There's only 2 groups of electrons around that magnesium, which means 2 groups of electrons means what Vesper shape? Linear. Did I draw this linear? No. So while this satisfies Lewis, it doesn't satisfy the 3-dimensional actuality of that molecule, and I should therefore redraw it and feel bad for having drawn it horribly. Those are chlorines. Okay. 2 groups of electrons. Okay. How would I explain the hybridization there? If I just use an s orbital for magnesium, that makes 1 bond. I need 2 bonds. I can now do a hybridization. I'm definitely going to bring in the s. I need 2 total orbits. S got rid of 1 of them. I add in 1 more p and I get sp. Okay? A little bit weird because it's a metal. Okay, so we're just going to kind of pretend. Okay, but the examples I could think of non-metals are more complicated. When we did that, what was left over? 2 p orbitals. Oof. Were left over. Man, that's extra gross. Okay? Looking at these 3 diagrams, does anybody notice anything interesting-ish about the sp hybrid orbitals?
Chicken legs.
They look like chicken legs. Okay, it's a fair observation. The energy? What do you mean? And I did hear you back. I'm going to come back to you.
It increases as you get more of the orbitals.
There's a reason we've got that little line on there. And if we look, where that center part is just a hair above the line with our SP. When we go up to our SP2, it's just a hair higher. We move up to the SP3, it's a little bit higher. Why? Why is the energy of that orbital changing?
Based on
How many orbitals you used, kind of, what did you say? Electronegativity is going to be a repercussion of this. Not the amount of electrons. The amount of p orbitals used. The s orbital and the p orbital are different in energy. Okay? If I just use 1 s orbital and 1 p orbital, the resulting hybrid orbitals are going to be the average energy of those 2, because I only had 1 piece each. So they're right in the middle. If I use 2 p orbitals, the average of that now is going to be slightly higher because I have more higher energy things going into that average. So we see a slight variation in the energy of those orbitals. Okay? That does have an effect on how that atom sees the world, because you're now changing the energy of those orbitals. Okay? That's neat. We'll see that repercussion later. I heard something about the direction they're aimed. Okay? The direction they're aimed is an attempt to draw 3 dimensions. May very well be a horrible attempt, but it's an attempt. Okay? What we're attempting to show is where those orbitals are in the plane. So if we got solid, solid. This one is clearly wedged, and this one's clearly dashed. Okay? And if we broke that down, if I looked at a molecule and I went, well, there's the carbon and the hydrogen, there's the carbon and the hydrogen, there's the carbon and the hydrogen, you would rightly probably say, what the hell are you drawing? Okay? That's really confusing. But if I tried to represent that with the orbitals, I think I heard the appropriate response back there. You'd be like, well, what the hell are you trying to draw? Exactly. Okay? These are an attempt to separate out each of those orbitals so we can see them approximately according to their wedge dash geometry. They will all overlap each other. They are all overlapping each other where they intersect at our nucleus ballpark. There, 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 and there. Okay? So when we get down to the bottom ones, okay, those ones would actually be somewhat easy to draw. So if we shaded that, there's that one. And we've got shaded that one. Somewhat easy to draw. Kind of, sort of. Everybody get that? Does that address your question?
I also had a question. For all the hybrid orbitals, do they also have a node like the p orbitals do in the center?
Okay. What is a node?
Place where electron can come.
Okay. How do we know there's a node? Okay. Said another way, you said the p orbital has a node. Where's the node in the p orbital? Okay. Between the two balloons. How do you know that's a node?
Because the balloon part is where the electrons can be and where they're floating around, the electron cloud. Yes.
It's not a repulsion. The balloon part is where the electrons exist. Remember, what we're seeing is this. Extra irritating if you're at home. Okay? That's actually what your orbital looks like. It's just a bunch of random dots. What are those dots? That's when we discovered the electron existed. Okay? The shape that we're associating with it is the 95% probability of finding it in there. Okay? So if I have a wider shape, what does that mean? Higher probability. If I have, and I can't really do this with an arrow. Oh, yeah, I can. A narrow shape, low probability. In this case, it is so low that it is 0, and we call it a node. Do we see that show up in our hybrid orbitals? Is there a node? Yes.
But why is there? Like, I'm not understanding why there's a node there. Exactly.
From the S orbital?
So why there's a node, I can come up with a really dickish response.
Go for it.
Quantum,
Okay.
which is actually kind of accurate.
Okay.
Okay? It's the quantum physics of the probabilities of how those electrons exist. We can do a bit of a hand-wavy option, and we can look at how these orbitals potentially overlap, okay, with an S and a P. Okay? This is where we bring in that positive and negative. Okay? Every time we get a node, we're transitioning from positive to negative. What does that node mean? Well, look at a graph. This is positive. Why? It's above the x-axis. Negative because it's below the x-axis. What is at that point? 0. That's the node on transitioning from positive to negative. Okay, and yes, that's 0. Okay? When we're going through and looking at something like this, what we're looking at is those positives and negatives. And that red case here, that's a lot of positive. Okay? So that means they're adding to each other. If they add to each other, how would I represent that? Wider balloon there. So we get a lot of probability kind of through here, right? Big, big, wide probability. Okay? What's happening down at the other end? They're canceling each other out. So I get less probability down here. How do I show that? Smaller. Okay? Because I still have that node in changing phase there, that's that node happening again. How would this get represented in my picture? That didn't erase quite the way I wanted it to. Right? A larger positive, a smaller negative. Right? That's all that's happening there. Right? Does the top lobe have to be positive? No. Does the bottom lobe have to be negative? No. Completely arbitrary. All that's important is recognizing that they're different phases. Not solid, liquid, gas. Positive or negative. Above the x-axis versus below the x-axis. That falls out of the quantum mechanics behind it. Okay? So, a little bit better of an answer, but still pretty shitty.
Good enough.
Okay? Kinda, sorta? Okay, so what we want to be able to do is to look at some compounds. We already kind of looked at BH3. What is the hybridization of the boron? SP2. How do we know it is SP2? There are 3 electron groups. 3 electron groups means SP2. So that boron is SP2 hybridized. Okay? That's a question. What is the hybridization of this atom in this molecule? Okay? We could also go through and look at what those hybridizations look like. It's ugly, it's awful, and it's a mess. But we're going to sort of attempt to push into that. Okay? So if I'm looking at that boron, we'll call it our blue boron. What happened to its hybridization? How? What should it look like in my diagram down here?
It should have 3 of the little drumsticks and then 1 regular p orbital.
3 little drumsticks. Where's that energy?
A little bit higher.
Okay. It's not exactly, I probably drew that wrong, okay, because I drew it directly in half would be even, so it should actually be a little bit higher than that. So we'll pretend that's a drumstick looking thing. Drumstick and drumstick, right? I think I started to drift. Okay, what's left over? A p orbital is left over. Okay. Ta-da! Yeah, like that's it. Not much else to it. We could layer in this and be like, well, but I'm actually concerned about the whole bond. In the bond, any one of those lines, is it just the sp2 hybrid orbital? What makes a bond? Electrons. Electrons from valence from atoms. Plural. 2 atoms. We just described boron. Where are the electrons from our hydrogen? We haven't shown those yet. What's the hybridization of the hydrogen? It's just an S, right? When we could be extra specific and say 1s. There's no reason to hybridize because how many groups of electrons are around the hydrogen? 1. Okay? So what happens is that hydrogen we'll call it red hydrogen in this case, comes in and it overlaps with one of those orbitals. Green hydrogen overlaps with another one. Would have been nice if I'd done this better sequence, but whatever. Black hydrogen overlaps with one of those. And when we're talking about how those things bond, that now moves into molecular orbital theory, which we'll look at in a second. So let's not break the bank yet. Okay? So those are now the orbits that explain that bond. What we're now trying to show here are molecular orbitals. Okay? Linear combination of atomic orbitals. In that little black box that I just drew, what did I do? I took two atomic orbitals and I combined them on a line. Linear combination of atomic orbitals. So we say LCAO followed by MOT for molecular orbital theory. The linear combination of atomic orbitals, that black box is now what? This is our molecular orbital. What made that molecular orbital? Okay? Atomic orbitals. Which atomic orbitals? S and P is too vague.
2s and 1p.
2s and 1p.
1s, 1p.
That becomes confusing. Are you talking about the second energy level s orbital?
1s from hydrogen. And
There we go. A 1s from our hydrogen interacted with from our carbon, we had
This one is
2p.
one SP2.
we had one sp2. This is one of the reasons why naming these based off of the orbitals that made them becomes tricky.
Where did carbon
See?
No idea what you're talking about.
I was like carbon, and he was like carbon. I was like, no.
Boron, there it is. See? No mistakes. Just don't rewatch the video. Okay? That's what contributed to make that molecular orbital. The 1s orbital from hydrogen and sp2 hybrid orbital from the boron. How about the next molecular orbital? The exact same thing, but sort of. But not the red 1s orbital. It would be the green 1s orbital. Okay? Because it's a different hydrogen atom. I saw at least one hand. Why is it sp2? What is the orbital in that black box that came from the boron? What is this orbital? It's sp2. Why did I write sp2? Because that's the name of that orbital. It's an sp2 hybrid orbital. That's why I'm writing sp2. Because it's not an s, it's not two p's. Right? Because an s and two p's makes three orbitals. I'm only using a third of those. Right? So it's an sp2 orbital.
It's just more of a label, right?
It's a label. How are we feeling? Some people are like, okay. Right? This overlap that we've created in here, I want to go back to purple. We've got an overlap here, right? That overlap happens directly. This is a direct overlap of orbitals. Everybody okay with that terminology? That makes sense? Okay, remember that. Because now we're going to delete everything. CO2. What's happening in CO2? What would the hybridization be of our carbon? This is now sp. What about the blue oxygen? sp2. Those lone pairs are orbits. There are three groups of electrons around that. And the purple oxygen? sp2 as well. So let's go ahead and start with our center carbon. What would our orbital diagram look like? 1s1p? I don't know what that means. So you don't have to apologize. Like 1s and 1p? So work with it. I know where you are. I lied. I do know where you're going with that, but give me the proper language. Because if we say 1s, 1p, that's what I'm looking at for my orbital diagram for carbon. Does that actually describe what we just wrote here? Because that is an S and that is a P. I need two sp orbitals. Not 1s, 1p, but I'm hybridizing 1s with 1p to make two chicken drums. That's going to haunt me this entire semester.
What was the wordage that they used to
Freaking chicken drums. Okay, and actually I'm going to ignore the shading. Okay, so there we go. There's two sp orbitals. Okay, that got rid of that one and that one. What's left over? Okay, our y and z. I'm just going to draw them both on the y-axis because the z-axis sucks. There's one. There's the other. You might be like, why the F did you just do that? We'll see that in a second. Okay? What about the oxygen? What's the blue oxygen? sp2. Okay, so that blue oxygen, in fact, I'm going to redraw that a little bit. Make it a little bit smaller, but put it up here. That blue oxygen, there's an sp2, yeah? We've got another one out here and another one out there. Do I care about those ones? Why not? They're not making bonds. So who gives a F? They're there. What's left over? Remember, this was an sp2. What's left over? 1p orbital. Might be seeing something here. What happened with our purple one? Drew that way too big. That's an eraser. God. Right? And then a leftover p orbital. Right? Because we got those. Yeah?
Shouldn't the red nodes overlap?
Should the red nodes overlap? Yes. Which picture do you like better? Okay, you like above. There you go. That's why I'm doing it that way. Okay? Okay, because if we continue this, remember, we still had the p orbitals left over. Z. Okay? You, and just for the record, you asked. Leftover p orbital and Z. Leftover p orbital. Oh, yeah, that's why I'm doing it this way. Let's take a look at the overlap. We'll color the overlap in black. We see some overlap there, right? Overlap, two orbitals. What did that make? A bond. Fantastic. Two orbitals overlapped over there. What did that make? A bond. What we just described is that bonding pattern up above, right? Now we have black bonds. We've explained each of those sides to each oxygen. Our diagram shows how many bonds? Another bond. Could I put more electrons in that bond? No, that's one molecular orbital. I can only put 2 electrons there, which means I literally can't put any more electrons there. So I have to put the electrons somewhere else to allow for a bond. Well, where's the somewhere else? The p orbital's up here. Does anybody see that direct overlap? No, that's because there's no direct overlap. Okay? That black shading was a nice direct overlap. The green one isn't a direct overlap. But electrons have this funny little ability to, yes, move, but more importantly, to tunnel. Okay? Why do we have to tunnel? What did that lack of space mean? What did that lack of space mean in there? Zero probability of finding the electron. What does this lack of space mean? No probability of finding an electron, which means can't overlap, and that means no bond, except electrons can tunnel. They can move through space where they're not allowed to be. Okay? Why? Quantum. Okay? So what does that mean for us? As long as these orbitals are in alignment with each other, the electron can see it and go, I'm jumping. What do I mean by alignment? Here's a p orbital, here's a p orbital. Do you see the alignment? Some people are like, maybe. Do you see the alignment?
No.
Do you see the blue pen? What was that? Just a little bit, okay? That's why we have alignment. The blue pen has disappeared. Do you see the alignment? Now there's no alignment. No alignment means you can't tunnel. Only when they're aligned do you tunnel. So when we're looking at this diagram, and this is where we get to play around with x, y's, and z's, if we said this was the y orbits, those y orbits are now allowing for tunneling as long as this blue one is y and that red one is y. Now they can tunnel. By tunneling, we're now sharing electrons from blue to red and red to blue. By tunneling, we now have formed a bond. There's the second bond. Okay? That indirect overlap allows me to get a second bond. What happened on the other side? Same thing. Really? Those are y orbitals?
Different axes.
It has to be off of a different axis. Okay? Remember our p orbitals are alternating by 90 degrees away from each other? That red one that I've drawn is actually on the z-axis, which means that purple one is also on the z-axis, which means they are now in alignment, which means we can now make another bond and we get that indirect overlap. We've now shown the existence of multiple bonds. That is where they come from. So when we were talking about in bonding types in Gen Chem, you were like, there's single bonds, there's double bonds, and there's triple bonds, which makes you think there's this thing that is a single bond, and there's this thing that is a double bond that is different. And that's entirely false. That's not true at all. There are sigma bonds, and there are pi bonds. A sigma bond involves the direct overlap of orbitals. What type of orbitals have to be involved to get a sigma bond? That's an s orbital? Some s-type orbital has to get involved. Funnily enough, sigma begins with s. Okay? A sigma uses s-type orbitals. Type being in very big quotes. Okay? Because we're referencing hybridized orbitals that involve s. sp is an s-type because there's s orbital in it. Okay? It doesn't have to be a hybridized orbital because it could be an s orbital. In the case of our borane, that formed a direct overlap. What happens with our indirect overlap? What orbitals did we use to determine that?
P orbitals.
Those were our p orbitals. So let's follow the logical pattern. Our s-type orbitals made sigma bonds. Our p-type orbitals will make pi bonds. So when I've been stumbling and saying multi-bonds, and you might have been hearing me say pi, when we're talking resonance, we're allowed to move pi bonds. Pi bonds have the ability to jump. Why?
Indirect.
Can I just get you to hold that up for me? Cool. Higher. Higher. I'm just kidding. Okay? Look, right? There's a direct overlap. If I add in a third one, now what can happen? An electron on the blue one can jump from blue to black to red. That is resonance. What if that happens? Now it can only jump blue to black. So when we're looking at resonance diagrams, thank you, when we're thinking about those resonance structures, what's happening is you're getting p orbitals stacking in alignment, which allows the electron to jump all the way across. That's what's happening in resonance. That's why we move multi-bonds. Why could we move non-bonding pairs? What do the non-bonding pairs move into?
Bond.
Careful.
Empty shell.
Be very, very specific in your references is a better thing. Not just bonds. What did they move into?
A py orbital.
They moved into, yes, into pi bonds. When you're doing resonance, all you're moving is electrons through a pi system. Okay? Why are we allowed to move them through a pi system but not a sigma system?
The sigma is a direct.
When we look at that sigma, it is that direct overlap. How can it jump from here to there? It's already directly evolved there. Right? We can only jump through that pi system. That's really neat. That's the power of molecular orbital theory. Okay? When you get really nuanced in it, it becomes even more fancy and crazy. Okay? But that's what we're trying to do. How do these orbitals interact and allow for the physical phenomenon that we know to exist? Okay? Because someone asked about it, we could do that. I don't even know what that looks like anymore. Looks like my kid tried to draw an elephant. Maybe an airplane. Flowers. Flowers are better. Okay? We can try and represent that with all of those orbitals at once, and it becomes a giant freaking mess to be able to distinguish. Digital images do a great job of it. This is why your textbook attempts to show them. For those of you being like, the textbook don't look much better than that. I agree. But that's the best that we've got. That's why we try and break them out into these smaller steps. So what molecular orbital theory and hybridization bring to the party is that we don't have single, double, and triple bonds. We have sigma and pi bonds. There's only two types. So how do I get the quote-unquote double bond? I need a sigma bond and a pi bond. How do I get a triple bond? A sigma bond, a pi bond, and another pi bond. Could I get a quadruple bond? Why not?
Ran out of p orbital.
We wouldn't have any more p orbitals to make that overlap. Okay? In organic chemistry. You could theoretically do it in inorganic chemistry because we lie. Inorganic is now moving down into all of our metals. What is special about those metals in comparison to carbon, nitrogen, oxygen? D orbitals. When you introduce those d orbitals, you now increase the odds of getting yet another potential overlap that could allow for more bonds. Okay? That's starting to jam a lot of electron density in one space, which you then start running into issues of electron repulsion and why we typically don't see those things. Okay? Neat. Was your laughter sarcastic? Sounded like it. Yes.
Wait, so in resonance, so a y, say it's in a pi bond in a y-axis, can it jump to a z-axis?
No. So the electrons in this blue py will never see the electrons in the purple z because they're in a perpendicular orbital. Okay, that phrase, perpendicular orbital, is a phrase I say a lot in second semester, and students just roll their eyes at me. Okay, because they didn't remember what happened with molecular orbital theory, which is fine. You don't need to know it. But the explanations for why things stop working usually comes back to molecular orbital theory. Okay? So we have to maintain that alignment. Okay. We address that. So, interesting results that come out of this. If we were to look at Lewis structures for each of these, okay, we could do a little race. Everybody should be able to draw these.
Sir, can I ask you a question?
Yeah, go, ask away. You just... I thought you were serious, you jerk. you should be drawing something roughly similar to these. Note for the red and the purple ones, I didn't show those kind of hard angles on them. Why not?
Wait, what?
We look at the black one, right? I'm showing that kind of pseudo-tetrahedral shape.
Yeah.
The red one's not showing that, right? Okay, so let's tweak it. The left half is how I drew it. I did not show it like this. Where's the right half? Why not?
Hybridization.
I'm attempting to draw the molecule as close to the three-dimensional representation as possible. Some of that comes because I have that aforementioned knowledge on how to assemble that so that I can draw it properly. Okay? Is that going to be really important? Do you want to pass? Okay? Yes. Drawing it accurately will change your interpretation. It will drastically change how SmartWork will grade you. Okay? When we drew out the purple one, you notice I didn't draw the hydrogen aim straight up. Again, I went straight out because I was able to more quickly recognize the hybridization behind this. Okay? So it was a bit of a cheat to make it a race because I knew the answers. Go figure, right? Okay? What is the hybridization of each of the carbons? What is it in black? SP3, right? And SP3. What in red? SP2. And purple? SP. The question followed up with this is the percent S character for the carbon. For the black one, what is the percent S character in that orbital?
25%.
It is 25%. There are 4 orbitals that went into it. One of them is S. 1 out of 4, 25. Red? And purple. Why does that affect our molecule? Okay. One is 50% S, one is 25% S. What is the difference between S and that other, what's the other orbital? P orbital. What is the difference between an S orbital and a P orbital? A little bit to do with energy. S is lower, and I think where we're going with is ultimately smaller. Why is that smaller matter?
You can only fit so many electrons.
The sp atom is holding the electrons closer to itself than the sp2, than the sp3. What is that going to affect? Could affect the shape a little bit.
Bond length and strength.
Bond length, and then someone mumbled it over here. Electronegativity. Okay. The purple one is literally holding bonding electrons closer. That is the definition of electronegativity. What does that mean about the purple carbon? It is more electronegative than the red one, which is more electronegative than the black one. Okay? It's the exact same atom. Hybridization will change those bulk properties. That's a big deal. Okay, cool. It made it different in electronegativity. That's not going to be a big deal. All right, let's delete the middle one here. We're saying H to C, right? Electronegativity doesn't make any difference at all. So if I threw a compound that had carbon and hydrogen in it versus a compound that had hydrogen and fluorine in it, you're going to have the same response? You should be violently saying no. Why? Fluorine is more electronegative, yes. Maybe this will help if we spin it the other way around. Isn't that an acid? Yes. Why is it an acid? Fluorine is more electronegative than the hydrogen. If carbon becomes more electronegative as an sp, what does that make that hydrogen purple in comparison to that black one? More acidic. By a lot. Okay? pKa's of the black one, 50. pKa's for the purple one, 25. Close enough. Okay? That is a huge difference in acidity. So much so that we can remove that purple hydrogen through acid-base chemistry. We can't touch the black hydrogens. Okay? That's a really big deal. And that comes back to hybridization and understanding those implications. Okay? Really cool. When are we done? 45. 45? Cool. So, atomic orbital overlaps. We could go through and do this C2H4. We kind of already did these examples. Do you want to attempt to draw these? Okay. Maybe instead of attempting to draw it, we just look at our Lewis structure and we try and predict something. C2H4. Okay, you notice I screwed up the geometry. I didn't remember it, wasn't as comfortable with it, so I might go, that's a bad way to draw it. Change this a little bit. Okay. We could reference hybridizations. Okay, so there's our Lewis structure. Electron groups. How many electron groups are on the carbon? 3, which means its hybridization is? SP2. The other carbon? SP2. Cool, we got that. Hybridization of the hydrogen? S. Cool, we got that. What are the orbits or the atomic orbitals used to make each of those molecular bonds? Okay. How many bonds do you see? I'd accept 5 or 6. Okay. 6 is probably more accurate. Why? It's not a double bond. It's a pi and a sigma. So it probably makes sense to reference that as 6 bonds. I'm going to say both 5 and 6 are wrong. Like you always say it's wrong. Okay. Why? Well, let's look at this one. What orbitals were used to make that bond? And I'll make it a darker red. So I heard an S. You got to give me more characteristics than that. 1s. You got to give me more characteristics than that. So a carbon 1s orbital was used to make that bond? No. Okay. So when you tell me 1s, should you be that specific? Yes. Okay. And what else? Okay. A carbon that was SP2 hybridized. Yeah? What was used to make this green bond? The same thing. If they're the same bonds, to answer the question, I really only have to know 3. Okay? Selective, could you go through and label the other ones? Yes. You just get the exact same answer as the red one that we just did. Okay, so let's take a look at the green one. What do you think was used to make the green one? So you should be able to give me a really quick, easy answer. Carbons were used to make the green bond. Yeah, okay. We've used some really silly answers, right? Feel free to just shout them out and be like, oh yeah, covered the nice easy base. What else was used to make it? SP2s. I'm going to say you're wrong. Damn it. You're always wrong. Okay, so let's look at the blue one. Maybe the blue one will make it better. Carbons again, right? I got rid of the easy answer. What orbitals were used to make the carbons? The blue one. Now you're like, I was wrong for the green one. I'm not entering that trap again. Okay. Which one's pi? Which one's sigma? You want to do that gesture again? Which one's pi? Which one's sigma? What does the shrug mean? Screw you, Mike. Okay. Creative license. The shrug did not mean screw you, Mike. The shrug meant you can't tell a difference. It doesn't matter which one, as long as you label them both. And that is a phenomenal shrug. Right? That is exactly what it is. You can't tell the difference between sigma or pi. Right? The drawing does not differentiate those. You differentiate them by writing. Okay? So you weren't wrong to say the green one was a hybridized one. Okay? Unless I arbitrarily said the green one was the pi one. That's arbitrary. Does that make sense? Okay, so do you want the green one to be the hybridized one? Yeah, okay, fine. Which hybridized? So now you're like, ugh. It's kind of hard to figure it out now, right? Because what happened with our drawing?
Half of it went away.
We use selective vision to delete that. Okay? That selective vision we need so that we know how many electron groups there are, so that we know the hybridization of those carbons. We don't actually have to label them, but we do need the information to specify how many groups of electrons. So dotted, right? What was the hybridization for each of those carbons? SP2. Okay? What's the bond for the pi bond? What orbitals are used? P orbitals. The blue one in this case we're specifying as the pi. The green one we're specifying as our hybridized sigma bond. Yeah? We feeling a little less shaky maybe? A little bit better? Okay. We could have kept the hydrogens, yep. All I was trying to do was simplify our understanding here.
If the hydrogens are there, can we just assume?
Yes. You should be assuming those hydrogens are there.
Wait, so the sigma bonds hybridized?
Sigma's hybridized, yes. Okay. So what does the textbook go through and do? The textbook did exactly what we just did. We said S and sp2, which we said was the same for all of those hydrogens. We just chose to ignore them. What did we say happened for the sigma? sp2 and sp2, direct overlap of orbitals. And then we left over our p orbitals. We use text to describe them. They use pictures. Does that image make a little more sense to you now? Okay? Okay. What does this ultimately mean for us? So this is an interesting one that we kind of talked about or sort of addressed. What happens if we change our view on this molecule? So this is going to be bizarre, so work with me here for a second. I'm going to grab this carbon with that big black dot. Black dot's a bad idea. Red dot. Everybody see the red dot? And I'm going to grab that carbon and I'm going to pull it out of the board at you. Okay? We're going to attempt to draw that with one big, well, not one big exception. We're just going to attempt to draw that. There's that big red dot, right? Okay. To the right, I'm going to have that purple sp2, and I'm going to have that red S right here. Yeah? To the left, I'm going to have another one, sp2, that S. Everybody okay with that? Where's this guy? Up and down, right? What's happening in the back? The exact same thing, just backwards. Okay. Do electrons want space to move?
Yes.
Okay. If you ever question that, okay, envision that when you came to class, you don't get to sit in a chair, you have to sit in a cardboard box. For those of you who are laughing, it was like my home. That would be very stressful, right? You want at least the perception that you could move anywhere. Same thing's happening for the electrons, which means when we copy that backwards, what we're getting is that system. Right? With the sigma bond, where they directly overlap, right? There's a sigma bond, cap to cap. What happens to that sigma bond when I twist?
Still a signal. Righty.
Does anything happen? No. Okay. So that sigma bond can freely rotate. There's nothing that changes. How about the pi bond when I twist?
Yep. I like it.
Now I've changed where the electrons can exist, because now the electron can't jump. Does the electron like that? So it says don't twist. What does that mean about pi bonds?
Stronger.
They can't rotate. Sigma bonds can rotate, pi bonds cannot. Okay? Of course, there's always ways you can break that, but okay, at our first level, sigma bonds allow for free rotation. This is one of the things that made Lewis structure so difficult, right? Okay, which I don't think we talked about in class as an example. But this compound, assume those are hydrogens, is the same as this compound. Why? Free rotation. Okay. If, however, I make this structure a little bit more complicated, and I'm not going to draw all the freaking carbons this time. These two structures are now different because that pi bond prevents the rotation. I am not allowed to grab this carbon and rotate it down that direction because the pi bond prevents that. That's going to vastly complicate / simplify structures when we're analyzing for differences between compounds. Okay? Where did that come from? Molecular orbital theory. Okay?
But it's still double bonded.
It is still a double bond.
So
Yep.
how does that affect the p orbital?
The p orbital prevents the rotation. That's all it does. Okay? It just says you cannot rotate, which means those two structures are now inherently different. Whereas in a similar case, they were the same. All it was a rotation. So sigma bonds I can rotate because of that direct overlap. Pi bonds I can't because the instant I rotate it, I lose that overlap. And that is a higher energy state. Okay? So, with our double bonds, that means we get the concept of cis versus trans. Cis meaning our groups are on the same side, trans meaning they're on opposite sides. So when I go through and take a look at this double bond, I have these two R groups. Where are they relative to the double bond? They're on the same side, cis. I heard a below. Okay, they're above. Are those structures now different? No, because what could I do? Take the structure and I three-dimensionally flip it. That was a bad direction to rotate my arm. Okay? And they're the same. So one of the things we have to be aware of is while the bonds may not be able to rotate, the entire structure can. You're responsible for all of those permutations. When we move to the other one, what happened? There's our R groups. Where are they with respect to the double bond? Opposite sides. And we get trans. Transcontinental Railroad did what? Both sides of the ocean. Okay? We're on both sides. Okay? Continent, not the ocean. Whatever. You know the picture.
Railroad on
Okay? The other thing I do want to kind of address here is because while we're talking about two R groups, what is this? Cis or trans? Actually, neither. Okay? It doesn't fit the pattern. When we're talking about cis and trans, they're on different carbons of the double bond. Okay? So this is neither cis nor trans. Okay? So we could go through and look at some examples on deciding cis or trans isomerism. Let's take a look at this last one. What do you think? Cis or trans? Like there's no R group. What does R mean? Okay? It's attached to something else. A better definition for R is it's something that is not hydrogen. How many R groups are on this structure? Attached to something that is not hydrogen. Did I say hydrogen? Good. The one there I thought I said carbon. There is one R group. To have cis and trans, what do I need? Two. Cis or trans? Neither. Next one. Why is this one particularly irritating? How many R groups are there? There's 4. When we talked about cis and trans, we're referencing 2. There's 4 R groups. Cis and trans, as a rule, doesn't work well.
That bottom one? The R.
Okay? Because it's not a hydrogen. Anything that is not a hydrogen. So that becomes difficult to label as cis and trans. This is where cis and trans as a term becomes very tricky. It's the reference of any two groups. How are those two groups oriented around the double bond? Trans. Whoops. How are those two groups? Cis. If you've got more than two R groups, cis and trans becomes very ambiguous. Very ambiguous. Not recommended to use. The first one was neither, or the last one was neither, and then this is just not recommended. Okay? In theory, we'll address what we should use instead later. How about we move to the next one? There's our double bond. R, R, R. This is, again, better to say not recommended. Okay? For those of you that know more advanced rules, that's okay. That doesn't change that these aren't not recommended for cis and trans. The very first one, what do you think? The R groups are on the same side of that double bond, yeah? So that would be cis. If we're going to label it as cis, we're labeling it as cis because there's a trans. Okay? That's why we do it. So we're extra clear that we're looking at the cis version and not the trans version. Okay? That's the point of cis and trans. Okay?
So in this case, R represent anything except hydrogen.
Yep. So that is cis. Could it have been trans? Why do you say no?
I don't know. State side of the law.
Okay. What would need to happen for it to be trans? Right? What the?
What is that?
Okay. What is that? It's the same thing, but it's trans, right? 1, 2, 3, 4, 5. I put too many carbons in, didn't I?
Yeah.
Damn. It's not going to get any pretty for those who are being like, oh, yeah, you screwed that one up. 1, 2, 3, 4, 5 carbons, 5 in a ring, pi bond, methyl. That's the trans version of that. Why are you laughing? That's weird. Why is it weird?
Because it doesn't look organic chemistry. I've never seen that before.
Someone started to say it. What? It's not possible. You can't physically organize the atoms to allow the ring to close with them being trans. It's not physically possible. If it's not physically possible, can the trans exist? No. Does it make sense to call that one cis then? No. The reason for cis and trans is because you have one cis and one trans. That's why you're using it to differentiate. If there isn't something to differentiate, why do you need to add extra words? Okay? So with some ring structures, chapter 4, okay, we won't be able to rotate, which means we don't need to reference it as a cis double bond, because it by default will be cis. It can't switch to trans. Okay? Is it possible that we could get a double bond in a ring that could oscillate between cis and trans? Yes. What do you need? Enough carbons in the ring so that you get enough wiggle room that you could have either conformation. Okay? Those of you with model kits, start adding carbons into it and see if you can get difference and find out where that line drops. Okay? Yes?
Isn't, like, so on the second one, isn't the top part the V? Aren't there carbons on either end of that?
So, and this is where cis and trans becomes questionable as a system. Cis and trans refers to any two groups. Right? We look at our examples, R and R. R and R. There's two R's. What happens with the middle three examples? Middle two examples. How many R's do we have? More than two. So the labeling of cis and trans becomes questionable to use because which two R groups are you referencing to say cis and trans? Okay. Is there a nomenclature system that, say, ranks groups by priorities? Of course. With that information, could you go through and say the higher priority groups are cis and trans? Yes. Okay. Do you have that rule set? No. So don't worry about it. Okay? We could consider cis and trans with that extra rule set. If we don't have that rule set, assigning cis and trans is a bad idea. Yes?
Where the carbons at the ends of the molecules not also being labeled as R groups? Is it just the ones directly next
The
to
R groups that we care about is only where it directly connects to the pi bond. Yep. That's where my transition is. I don't care what happens afterwards. As long as that atom is not a hydrogen, I can label it as an R. Believe it or not, that actually simplified a lot of cis and trans. Okay. It was all in the video. Let's see what you guys can do in like a minute. Oh, Jesus. There we go. It's that optimism, yes. Yes, I can definitely get this done in a minute. If I'm going to take molecular orbital theory, but now I want to see how p orbitals can interact with each other. Okay? What axis do I want to have these two p orbital atomic orbitals interact on? Do people say Z or same? Same. Okay. I'm not about to draw this on the Z axis. Okay, same axis. Which axis? X. Okay. Okay, this becomes a little bit becomes a little bit weird. What? What the hell's going on? Fine. X, Y, ugly Z. If I bring my X orbitals together first, what's the first thing that's going to interact? Or bring these two atoms together on the x-axis, what's the first thing that interacts? So hence, X, Y, Z. What's the first thing that's going to interact when I bring these together on the x-axis? The X orbitals. Remember, a p orbital, like that. So there we go. We could get that overlap, yeah? P orbital could be positive or negative. Positive or negative, yeah? If they're both positive, what happens? It gets bigger, okay? The nodes are still there. So what happens is I get this space, like that, yeah? And a little bit of node at the end. That look good? What have I done to the electron density between the atoms? I've increased it. What does this look like then? A bond, right? More electron density between atoms. What happens if instead of it being positive with positive, it was negative and positive? They cancel out. Okay. Note, in this case, I have a new node where the electrons can't exist because they've canceled each other out. Note, I've also placed that higher in energy. Why should that be higher in energy? Less places the electron can exist. Is that also a bond? What makes a bond? Sharing of electrons where? Between two atoms. Can I have electrons between the atoms? No, so that is not a bond. Okay? Is that not a bond? Or is that the opposite of a bond. It is the opposite of a bond. We are actually keeping those away from each other. So this isn't not a bond. This is anti-bonding. I need a new not. Okay? Is that still a possible orbital? What did I bring together to make this? Which p? 1x and 1x. So I brought in two atomic orbitals. How many molecular orbitals must I make? I must have the same number. I just showed one as a bond. I showed one as an antibond. Is the antibond a molecular orbital? Yes, it is. Why is that important? Okay. How many electrons fit in each orbital? 2. So if I put 2 electrons in here, what would I think about the interaction between these two atoms? Did they form a bond or not? Yes, they formed a bond. What if I put 2 more electrons into the molecular orbital?
Cancel out.
Not only does it cancel out, our antibond is higher in energy than our bond is lower in energy, which means the net result of putting the electrons, 4 electrons in both of those, is that my net result is an antibond, meaning
It will bond.
that bond breaks. We're done.